2P2. This project is a research project, a collaborative one between several universities in Europe. University from Aalborg, Mondragon in Spain, and Czech Republic at Liberec, and of course, University of Toulouse. So today's seminar focuses on the topology optimization applied to the electromagnetism systems. It will be presented by Professor Frédéric Messine. He is professor at the National Polytechnic Institute of Toulouse. This presentation will be recorded and will be available later on the R2P2 YouTube channel. So you are invited to ask questions all along the presentation, so do not hesitate to interrupt our speaker. And so it's time for me to let you with Professor Messine starting his presentation now.
So thank you, Francois. Yes, today I will speak about topology optimization in electromagnetism. Is a kind of introduction. I will share my screen. Okay. So that's it. Is it okay? Can you see my main screen or not?
Not it's in the presentation slide.
Yes. Okay, that's not good. So excuse me, I have to test a bit. Okay, this one is better, I think. Yes, sure. I have not the habit to use PowerPoint. I'm sorry about that. So I'm Frédéric Messine from Toulouse. I'm a colleague of François Pigache. I did this work with some of my colleagues, Carole Hainaut, who is now a professor in University of Montpellier, and also some students, Tafa Sanogo, Younes Artemi, Alberto Rossi, and also Dominique Arribet and Raphaël Villamont. So today I will introduce you what is topology optimization, what is this kind of optimization, which is a bit particular, okay? And I will show you how it's possible to design some actuators using this tool in electromagnetism, and we will speak about thruster. So the outline is okay. This one. First, I will speak about the design and optimization, just to be sure that everyone, okay, can understand what is the design of an electrical actuator or of electrical machines, for example. We will speak about that. What is optimization? What is the link with the design, okay, in electromagnetism? The second part will be about topology optimization in mechanics, because the topology optimization was born in 2000 to solve mechanical problems. Okay, at the beginning, that was in mechanics. Okay, so I will introduce you what is topology optimization, the difficulties and the methods and algorithms, and in the third part, I will show you how it's possible to solve problem in electromagnetism, mainly about the application to design all effect thrusters, but it's a bit more general in electromagnetism. Okay, you can stop me everywhere, you know, you can ask me a lot of questions that will be much more dynamic, and okay, it's better for me, I think, so maybe I can leave also sometimes at the end just to discuss with you, okay? So do not hesitate to ask me some questions. So first part, just a bit an introduction about the link between design and optimization. So using electricity, you can make some movements, some actuations, okay, like this, and you know, it's you can use the electricity to make movement, or you can use movement to make electricity. Generally, I do in this side, okay, I use electricity to make movement, and I have to design electrical motors or electrical actuators. Okay, and I'm a mathematician, I'm a specialist about optimization, but I am in a Laplace laboratory about physics, and all my colleagues are physician guy, good researchers in electrical engineering. And okay, we share a lot together to make those kind of designs better. So I will show you a bit the link between the design and optimization. For example, for a Zoe Renault, okay, you can try new motors, for example, those kind of motors with just iron in the rotor, and you can make some new rotors like this. That's the best, one of the best rotor that can be made by an engineer, okay, a very good PhD student, okay, and we can optimize it, and you can see the shape and the form are a bit different, and they are optimized. But in that case, it's kind of, it looks like a topology optimization or shape optimizations, because we change the shape and the topology of this kind of rotor, of course. But in fact, we just modify a bit the thickness of some parameters. Though at the end, that's for me, for the mathematical part, that's an optimization problem, a parametric optimization problem. We just change some parameters about that, and we use a code, an optimization code, to solve this this problem, and we increase a bit the torque, and we decrease a lot the torque repowering for that kind of motors. But you can see here, it's kind of shape optimization, not topology optimization, because the topology is quite the same. You have the air in the same place. You have the number of flux barrier in that the same number of flux barrier. You don't change a lot the topology of those kind of motor. So you have to keep that in mind. Okay, that's a first example. So generally, you know, the design of actuators are inverse problems. Okay. In fact, you have an electrical motor like this. You have to solve the Maxwell equations, for example, those kind of Maxwell equations. Okay, and you can find some characteristic values with the potential vector A and the magnetical field B and the torque T. Okay, but in fact, to design, you have to solve the problem in the reverse way. You know, you have to fix the B, the magnetic flux, or maybe the torque, and to minimize maybe the mass or minimize the volume. So you can understand that you have to solve the Maxwell equations in a kind of an inverse way, you know. And what you want to have is all the design of your best electrical machines, okay, or electrical actuator. For example, here you have the diameter, the length of the machines, etc. Plenty of parameters of some angles. You can do more general inverse problems of design, you know, by considering plenty of different kind of stuff inside. Maybe you can put magnets or not inside, or coils inside the rotoric part. Okay, you can change a lot the structure of that. So if you have analytical models, for me, for a mathematician guy, you have to minimize, for example, the volume of some parts of the motors, for example, the volume of the magnets here, and also the Joule losses. Okay, you have other equations. Of course, that's a nonlinear problem, but you know that's a parametric optimization problem, okay? Because you will move just the parameters, the diameters, for example, here, some thickness, okay, the air gap, E over there, between the rotor and the stator, okay? You have this, and you solve this, this problem. That's a parametric problem, but you can see here the link between the design of an electrical machine, for example, and the link with solving an optimization problem. An optimization problem, a global optimization problem, we can find global solution, okay, using different algorithms. I put some example like here. Okay, doesn't matter. An example that we solved for Mitsubishi, it's okay, you have to minimize about 14 parameters. Parameters are the diameter, the length, etc., some angles, etc. You have to compute the torque here by finite element methods, okay, and the average torque must be about 5 Newton meters. You must have a torque ripple less than 5% and the temperature less than 105 Celsius degrees, okay? So we have plenty of constraints, and it's just to show you what kind of problems I have to solve for parametric optimization and the link between, okay, the design and the optimization. So in the center, you have numerical optimization, numerical solver. You can select some machine you want to optimize, you know, you can select solvers to optimize them. And okay, after a while, you will find solutions. That's an electrical machine that we designed for Mitsubishi, okay, and we also construct it, we validate the solution, and okay, and you can construct it and to prove that this machine is okay. So that's the end of my first part. Is just for you, just to have in mind the link between the design and optimization, because that will be the case for all my talk this morning. Okay, do you have some questions? I can, in that part, I think it's quite simple for everyone. I hope so. Okay, so we can pursue. Now, second part, I will speak about topology optimization, first in mechanics, because it was born in mechanics. So at the beginning, you know, those kind of mathematics came from physician part, from mechanic part, you know. And that's often the case, you know, plenty of mathematics born in physics. So that's interesting to notice that and to introduce what is interesting and what is topology optimization in mechanics. So, of course, first some design. You can see here the, okay, what can do topology optimization? You can design the structure of a motorbike, you know, and you can minimize the weight of this motorbike. Okay, that was made by Airbus, and they use a 3D printer from Siemens. Okay, and you can see the structure is very thin, and we minimize the weight, but you must have some stiffness and rigidity of your motorbike, of course. So it's very weight, but also it's rigid enough, you know. You have to understand that. That's the same for some powerful car, also Bandita, and everything is printed. All the structure was printed with a printer, 3D printer. So now, what is interesting, you can see that all the design are very optimized. You know, we are very far from what human can do. Okay, okay, that's kind of skeleton, something like that. You can see, and the structure is very rigid and very thin also in some parts, and the weight is okay, minimized. Okay, so that's a design problem. And using topology optimization, you have to find those kind of solution. You can see that's kind of bone that looks like maybe human structure, something like that. For some mechanical parts, you can see what we did already and what we can do using a 3D printer with plenty of small beautiful meshes like this. And okay, the rigidity is improved and the mass is minimized, okay, of those kind of objects. Of course, it's very difficult to make using normal normal way to make those kind of parts, mechanical parts, of course, okay. But using a 3D printer, we can do those kind of things. Just to speak about a software, OptiStruct is a very good software and used. It was used to design the motorbike, and I think also the car that I showed before, you know. And it's mainly used by Airbus and Boeing also to design some part of the wings, you know. In the wings, you have those kind of parts here, and this part has to be, okay, you have to minimize the weight. You are in a plane, that's very important. And of course, you have to have some stiffness, some rigidity of this structure, okay? And you can design it using this software. I think I have some, okay. Well, I thought that I had some example, but maybe after, okay, maybe after. So yes, I can show you some example of the design of wings. You can see here, those kind of structure, we can make it so, but the first idea was done by a topology optimization software, you know? You can see here, I just cut it from internet. You can put on internet topology optimizations and aircraft wing, and you will find this kind of design. You can see the interior of wing of this. That's difficult for human to make those kind of curvature, but that was designed by a topology optimization software, and you can, the result is around 1,000 kilo of weight saving per aircraft. So that's very, very huge. The gain are very huge compared to what very good engineers can do. Okay, some definitions that came from Wikipedia. Topology optimization is mathematical methods. Okay, you can see mathematical. So I will explain why it's mathematic. Okay, I will define it. That optimize material layout within a given design space. Okay, for a given set of loads, boundary conditions and constraints, etc. So topology optimization is different from shape optimization and sizing or parameter optimization that I explained you just in the first part of this talk. Okay, in the sense that the design can attain any shape that you want within the design space. You know, you can have what you want. You can see for the car here, you don't have to fix anything. You have all in plenty of parts to win weight, you know, and that's the same for the motorbike. You can put holes when you want, okay, and all the you don't have to have a red lines, right line, sorry, okay. On that, you have plenty of curvature for that if you save, of course, weight, okay. That's the idea, and you can generate some holes everywhere, etc. Holes, okay. That's not the case for shape optimization. Shape optimization, you will just optimize the shape of the form, you know, and that's it. You will not change the entire part of the form. You will just optimize a bit the shape. I will show you some example after, okay, for thruster. Just a bit of history that's in Wikipedia, but in the French part, I just cut this. Okay, actually, okay, until recently, that was 2017, we cannot solve 3D models, okay, about 5 million of voxels. You can imagine we can solve problems of 5 million of elements. That was the case before 2017, okay? But a new program optimized objects about 1 billion of voxels. So now we we can solve problem with 1 billion. Okay, that was to optimize in 3D the wing of Boeing 777. Okay, and we win again 5% because, you know, for those Boeing, okay, the wings were already optimized using topology optimization for each part. And now we optimize it in 3D. And again, we win 5%. Okay, that required about 5 days of computations, okay, using, of course, a very, very huge computer, okay? Very efficient computer. But you have to you have to keep in mind that now in mechanics, that's not the case in electromagnetic, but in mechanic, we can solve problems in 3D with about 1 billion of voxels, so 1 billion of variables. That's very, very huge for an optimization problem, okay, in 5 days, okay, but it's not so bad, okay. Some examples in architecture also, you can see those kind of bridge, very beautiful bridge like this, and also some things like this, because using this, you just need three things to maintain the roof. Okay, you can have also beautiful bridge like this, and in the Qatar, you have the Qatar National Center, and you can see the structure which okay, maintain the concrete, okay, over there, and you can see the structure. It was obtained using topology optimization, okay, minimizing the weight, and you can see that's kind of tree, okay, that's kind of tree with some branch, okay, that's quite nice. So I will take this example, and I will explain you on this example what is topology optimization and the method to solve those kind of optimization and to solve very huge problem, okay? So we take 2D simplifications. That's just an example of the concrete here. And of course, we don't know here what I have to put to maintain those concrete above, okay? That's the floor, not the soil, sorry. Okay, first idea, parametric optimization. Okay, it's just, we can have the idea of kind of table like this, okay? You put concrete materials here, and you just have to minimize, in fact, X, okay? But you have that the structure will be sufficiently rigid to maintain the concrete above. So you have to make computation using finite element methods in mechanics to solve some mechanical equations over there. Okay, that's an introduction about what is also parametric optimization in that case. You have just one parameters. The parameter is just the thickness of this part, okay? But a human has to put an idea. Okay, the human has to say, okay, we can try this solution, and architect has to say, okay, maybe we can do this, okay? Another architect must say, okay, we can do maybe better if we put two things like this, and you have to minimize x2 plus x3, for example. But the structure has also to be rigid enough. You have now 4 variables, you can change, you have much more parameters, but okay, you need a human and an architect to find those kind of solution. You can find much more difficult solutions like this, okay? You can find plenty of different ideas. I put some of them like this, but it's just a kind of joke. And you can, of course, combine all those ideas to make maybe a very beautiful, okay, center, okay, a beautiful building. But maybe it's not the real optimal solution, because you impose the structure of the solution. You impose those kind of structure or those kind of structure, okay? You will find maybe plenty of solution if you have plenty of different ideas, but of course, it's not the best possible. So now let me show you what is topology optimization. Topology optimization is to find in this omega v, okay, is to find the best material distribution in order to minimize the volume of materials with respect to the structure is rigid enough. So in fact, what you have to say here, you have plenty of material points, okay, and rho will be the density. 0 is for air, for example, and 1 for concrete, okay. So if you see your problem, okay, you have to minimize, of course, an integral, but you minimize the volume of concrete, for example, that's kind of mass. And you have subject to, ST is for subject to, that the rigidity has to be strictly superior to a limit that I put K. And of course, rho are elements from 0, 1. You work in kind of space, okay, difficult space, because that's a distribution of material. You in each point you can have 0 or 1. It's kind of a distribution. So you find a function, but at the end the value of this function rho x y, you know, rho x y. You don't need the little I. It's a mistake here. Okay, it's the rho x y is the distribution of material, you know. So you have to find this distribution of material, and you have to find rho, and rho is in fact a function with 2 parameters, x and y. So you search in infinite space of functions, of course, of function which must have value, discrete value 0, 1, and so that's not so easy to solve in that step. So okay, so you have to find this kind of function, the distribution of material, and that's topology optimization, okay, with a constraint over there. So one idea is to first to discretize. I will discuss about idea to solve those kind of problem. The first idea is to discretize, okay? And for example, you discretize with a pixel, like there, that's little squares. And on this pixel, you will put some materials on it, okay? So 0 or 1, 0 everywhere, or 1 over there. So that's the first idea. We can discretize at the first step. That's a bit interesting because we can find first methods, first algorithms. Okay, I provide you the meshes of the Qatar building, okay, center. You can see we can do it in 2 dimensions. Okay, you have all the meshes of this beautiful national center. Okay. So first idea, this discretization of the variable region. So now you have to solve a discrete problem. So each rho is now just has just a value 0 or 1, okay? And to minimize the integral becomes to minimize the sum of the rho e, okay? That's interesting, but the rigidity function is still very difficult to, to compute. You need a finite elements method, something like that. You need simulation tools to evaluate the rigidity of the structure. Okay, that's the much difficult part, you know, because that will spend a lot of time. Let me take some ideas, because now it's a discrete problem, so it's a bit easy. So the first idea is to say, okay, we can construct all the possible combinations of points. You put 0 or 1 and you combine all of the possibilities. Okay, that's a kind of exhaustive algorithm. The problem is quite simple, you know, that's 0, 1, you can make those kind of combination. The name is an exhaustive algorithm. You test all the cases, okay? And of course, for all the cases, you test if the constraint is satisfied. If the constraint is satisfied, you keep this solution and you will keep the best one, okay? So the hypothesis is the simulation time, okay, that I denote TS n. N is about the number of points that you have, maybe, and if it's great, about 1 billion, like for the case of Boeing wings, okay. If it's a bit large, you know, that can change a bit the time of simulation, okay, but else it's a bit the same, okay. So if you want to test all the possible solution, you will have to exponent n time ts time to solve this kind of problem. It's a kind of order. Maybe it's a bit more, because, but not too much, you know. It's a bit more because you have also to make some comparison, but the comparison for a computer, it's nothing, you know. You have to compute also this sum, but this sum compared to the computation time that you will use to solve the rigidity problem, it's nothing. So the order, it's 2 exponent n time the time of simulation. So if I take n, for example, n equal 100, it's not very huge. It's just 10 by 10. You will have quite a big square. You know, it's not a huge mesh. You know, it's just 10 by 10. And if I take the simulation time about 1 minute, it's not so bad. Also, we can have time of simulation much more than 1 minute. It depends, in fact, but let's say, to fix the idea, 1 minute, okay? That will take, in fact, 2 exponent 100, you know, minutes, and it's about close to 700 days. So you can imagine, okay, the exhaustive algorithm, it's very interesting, but for a few number of variables, okay, it's global. You will have the very good solution, but you can see here, even for discretization about 10 here and 10 here, 100 square, you know, it's not maybe enough. Yes, because you can see here, you have plenty of little squares, okay, everywhere. It's not enough. That will take too much time, of course. You cannot spend more than 2 years to solve those kind of problems, okay? And so, of course, if you use a better computer, you can divide by maybe by 10 this simulation time, but okay, you will divide by 10. But we will discuss a bit after that what happens if I add just one more variable for this kind of algorithm. The second idea that was introduced quite early is also to solve this discrete problem, you know, by using meta-heuristic algorithm like genetic algorithm, simulated algorithm, because they are very good to solve those kind of discrete problems. So we can use them directly. You don't have to do math. And that's nothing is mathematics inside this. So in that case, you know, you have to take care, because when you use meta-heuristic algorithm, you fix, in fact, the final time. You fix the number of evaluations that you want to have. You know, for a genetic algorithm, you will fix the number of generations of points and the number of points you have at each generations. So, for example, if you take a limit about 1 hour, you will just test 60 points among, you know, you will just test this among 2 exponent 100, which is very, very huge, you know. If you take 1 week, maybe in 1 week, okay, you have to multiply by 24 hours and 7 days, you will, okay, test close to 10,000 points, and okay, among those, it could be okay, it depends, but okay. In 1 week, you can find a quite good solution maybe for that, okay? So what happened now but that's a bit a limit, because, you know, if I come back from here, if I just add one more variable, okay, here you can see here you have to multiply the time by 2. It's 2 times 1 exponent. It's 2 times 2 exponent 100, and so you just by adding just one variable for those kind of algorithm, you have to multiply the number of days by 2. So it's about more than it's about 1,400 days of computation just to add one parameters, you know, just one variable more, you know, one little square. So if you want to double the number of points here, you have to multiply 700 days by 700 days. You can imagine the number of days you need to solve this kind of problem. Using meta heuristic, because you fix the limit, it's still the same, but you know, you find points among a very huge number like this of possibilities. So if you increase the number of points here, that will be difficult with just 10,000 points to find the good solutions. Now we will make a step, okay, into the methodology of optimization tools, you know, in topology optimization tools. First, is to take the variables continuous. We will take the continuity of the variables. So you have to relax the variables. So now you will not find the solution which must be 0, 1. The solution could be in the interval 0, 1. So we do that, okay, because we have some advantages. We can compute the derivative, and from a point, we can see in where is the direction to have a better other point using continuous optimizations, you know. You can compute a step, an optimal step, you know, to decrease the value of the function and to find, of course, that's local optimization, but okay, you can find local solution like this. The difficulty is about the solution will be now a real value in 0, 1, and not a material or not air. So you have to deal with this. So we had another idea is to penalize, okay, the solution. We will penalize the solution if the solution is not 0 or 1 for a material point, you know. So it's kind of change of variables. So rho E is changed by PE, okay, and P is a penalization function. So I can show you some penalization function like this. Okay, you have some degrees, for example, in polynomial penalization functions, okay. If you increase the degree of the polynomial, okay, if it's polynomial 1, it's just a line, so you penalize nothing, okay, no problem. But if you penalize a bit more, you know, maybe with n equal 10, you can see that here that's a kind of density, okay. If you have 0 point right is very close to 0 over there, and if you have 1 over there, you have, that's about the permeability, but you have to think about 1. So if you have 0, you have 0, but for a long while, if you have 0.7, you have still 0, okay, for the penalization function. And if you have above 0.9, you will find 1, not 100, that's a permeability, but that will be 1 for us in mechanics, okay? You can find also exponential penalization function, the other kind of penalization function like this. That's the same idea. So you can see we can try at the beginning to keep the convexity of the function, and also because we need to minimize the weight of the structure, we prefer to say, okay, here if rho is equal to 0.9, you put materials, else we don't want to put a lot of materials. So we put materials when it is really needed, okay? Okay, exponential. You can take also arctangent. I use a lot of arctangent for the density here. You can see about 0.1 what happens with those kind of penalizations. So now you add this penalization function. You can compute the gradient, okay, using finite element methods. Of course, that's local optimization algorithm. You can take SQP, entire points, etc. Plenty of things. On this example, okay, the same kind of example, you have 1 minute to make one simulations. You can see to compute the gradient, you need in fact n+1. So here, 100 plus 1 time of simulations. This time is about you have to solve a linear system at each step, but it's nothing. You solve a linear system about a matrix 100 times 100 is nothing compared to 1 minute to solve this part. So in fact, to solve this problem, to have a local solution, you will need also 1 week. So it's the same again, like a genetic algorithm, but we have a big difference. The difference is it's now if we add one variable, you know, the variable is not in the exponent, it's not 2 exponent n. And so if you add just one variable, it's still close to 1 week. If you add 100 variables, okay, you have to double, you need 2 weeks. And so that's interesting to go through this way, okay, because, you know, the main part of the work is to compute just the gradient. And okay, and of course, maybe you need 100 iteration of the local solver, but that will be the same if you have 200 variables or 100 variables or maybe 1 billion of variables, okay? And so, of course, if you want to solve a problem with 200 solution using this technique, you will need 2 weeks, okay? That will not exactly the case for genetic algorithm because you will search solution into a very, very huge space. So the main idea now is to, at the moment, you know, we did not a lot of mathematics, okay? We have all the good ideas to solve that. We can solve a bit this problem with a few variables, few number of variables, 100 variables, something like that. And that take a lot of time, close to 1 week, okay, to have local solution. But if we go inside, if we enter inside the equations, okay, so this idea is first, we do not discretize, okay? We consider this problem at the moment, and we will do mathematics. We enter into the equations of R, and okay, we can using an adjoint problem. I will show you how it works after in electromagnetics. You have to solve an adjoint problem, okay, but you have to enter in the equations. You cannot use anymore different finite difference method. Okay, you have to enter in these equations, okay, and you can see the computation of the gradient. If you make this mathematical effort, you know, using adjoint problem, you know, the time here is just 2 simulations, the time of 2 simulations, okay? So the good idea is to do this effort, to enter into the equation, to do mathematics, to try to solve those kind of problems, to enter into the equations, mechanical equations here, to find the adjoint problem, to solve it, okay, and to construct the gradient by solving this adjoint problem. We will see in electromagnetism how it works. And doing this, you don't have any more n over there, you know, you have just 2. And you can see here, using this tool is just 3 hours of solving to find a local solution. And it's not depending on the number of points. If you put 200 points, that's the number just of iterations. That's not the number of points. You have to put 200 iterations. It will be close to solve a simulation problem with 100 variables or 200 variables. It will be the same, about 2 minutes. And you will stay at 3 hours, okay? And if you have 1,000 variables, you will be maybe 4 hours, and if you have 1 million of variables, we will be about maybe 5 hours, something like that. But that will be just close the same, you know. And, you know, using adjoint methods like this, you can find solutions, and you can maybe find solutions for 1 billion of variables. That's they did. Of course, the simulation time for 1 billion of variables is very huge. You have to execute to compute, to make the computation on parallel codes, etc. But at the end, you know, it's about 5 days. You increase a bit the kind of simulations. You have to make a very beautiful, of course, code, but it's not so difficult. So you can imagine here the two. You have never n inside. You have not exponent n, and you have not n plus 1 over there. Okay, the n disappear here, and that's why it's very interesting. But it's also that's why it's very difficult, because you have to write an adjoint problem and you have to do math. And okay, and that's why you need maths. So I will do I did this work in electromagnetism, and I will present this in the third part in just 5 minutes. Maybe I will show you an all effect thruster. So the all effect thruster is to design, in fact, the magnetical circuit over there. You have coils and ferromagnetic parts, okay, iron parts over there, and we want to design a bit those iron parts, okay. I don't have the time to explain you how it works exactly, that push ions over that. That's interesting, but I think I have to focus on topology optimization, sorry. Okay, so the thruster will have some propulsion of ions like this. You can see the structure. We make a simplifications in 2D. That's an axisymmetric structure. You know, you can make a cut, and you can see here the iron parts, also the coils, for example, those kind of thruster. And we want to design those parts, mainly those kind of parts, the pore parts, okay, of iron, because we need to have some magnetic field in some part inside the canal, okay, here. And what is parametric optimization? I can show you on this example. You can have some parametric variables over there. Shape optimizations, for example, for the pores will be about the design of the outside part of the shape. You can move a bit the shape of the structure, and of course, topology optimization. Now you know what it is for those parts. For example, for the pore parts, okay, for this structure, you have to discretize, but maybe not directly. That's not the good idea in a second time, okay? So, of course, I discuss a bit in that case, what is, we have some continuous variable, for example, for the coils, we can change the density of current, okay, and we have binary variables. Also for the coils, we can discretize the coils, and we can discretize the pore parts over there, you know, and we make continuous relaxation, penalization, you know that. I use mainly arctangent penalization function. Okay, so what I have to solve is those kind of problem in my side, okay, is to minimize, in fact, the difference between magnetic field that we want to have to the efficiency of the thruster. It's named B0, okay, and the magnetical field that we have to compute following the Maxwell equations that I give you here, okay. And of course, we want to make the gradient of f, to compute the gradient of f, and it's a bit technical. And okay, I will show you how it's quite rapidly, how it's possible to make the adjoint method. Of course, it's very difficult. That take a long while to explain in details what happens. I will need maybe 2 hours to explain each part of this, but I will show you that it's possible to do. Okay, what we need is the partial derivative in the continuous way, you know, from P or Rho if you prefer. Okay, depends if you use the penalization or not. Okay, in the direction phi, because phi can be any function and will give you the direction of the derivative. And so you have to make the derivation of the small function over the potential vector, and you have to make the computation of the potential vector over the material, you know. And okay, you can enter into the Maxwell equations. Okay, solve a bit that. I try to, okay, we will try to eliminate those parts, okay, and to compute those parts, in fact. And we can do this using Lagrangian formulations by introducing a new variable, okay? The variable is also potential vector linked to A, okay? That's a variable, but you can imagine that's a potential vector. And okay, you have to put it in kind of, on this case, in a kind of Maxwell equation again. Okay, you can write it like a Maxwell equation. Okay, where M is the magnet, which is between the difference with B and B0 in a particular region. Okay. So the sensibility is given by this. So at the end, you just have to derive your mu function, but it depends if you are in a linear case, it's quite easy, of course. If it's non-linear, you will introduce some different things like this, and it's much more complicated. Okay, but you have to derive this, and at the end, you can see the derivative is just BA, that of course, the direct problem, you solve the direct problems time the solving of the adjoint problem. Okay, you have to solve this adjoint problem over there to find B lambda, that's a Maxwell equation, and then you can reconstruct, in fact, the gradient over there. That's not in omega t, that's in omega, okay, in omega v for now, where the variable is. And it's also the case if you want to derive by g, okay? You just need the potential vector over here. And so you have enough information. Now you can discretize. Now you can make finite element method to compute B lambda, to compute BA, and to construct the gradient, okay? So for an optimization algorithm, you provide in an initial point, you know, you solve the Maxwell equations, the direct problem, of course, over there, and you will find A and BA using a solver, you know. You can compute with this directly the objective function directly, but also you can construct the adjoint equations given like this. I explained it to you just before. You can compute them, and using BA and B lambda, you can, okay, compute the gradient. And you take this gradient, you give the value of the objective function and of the gradient, and you take a descent, local descent algorithm. For us, we use a lot of time, fmincon of MATLAB, the interior point method, to solve that. Okay, so I do not discuss a lot about that. You have the equations over that. That's the main part, very difficult in mathematics. So that's the key to have very efficient topology optimization code. And of course, with my PhD students, Satafa Sanogo and Younes Ertimi, and also Carolino, we work a lot on on an efficient way to solve this, to have those equations, okay? And after that, I can show you some example. We can solve problem with plenty of meshes. It doesn't matter the number of meshes, is just take 1 hour of computation and that's it. You have local solutions, so you can make a multi-start optimization problem. You can take plenty of points and that's it. Okay, here I want to have some magnetical field precise fields inside this zone. That's why we designed this this part. You can see that's topology optimization. So also the solution you have all, maybe it will be difficult to obtain them. You have separate things like this, and okay, you have maybe the good idea of what is the solution that will give you for human the good idea of what's a solution, and then you need a next step to make this solution manufacturable. We can at the end we have to make the thruster, of course. So at the end, okay, I can show you, we can add plenty of more objective function, constraints, etc. We can say, okay, we can have 3 objective zones. We can complicate the game of design. We can complicate a lot the design. We do some design for Safran a lot of time, and that's really interesting. Okay, we can have plenty of things like that. Just to show you a kind of solution like this, it's difficult to construct, but you can take some points and you can make after that some shape optimization that will be also quite difficult to make a concrete thruster with this shape optimization. Okay, we can use Bezier curves to do that. We can also do parametric optimization. Here you can define plenty of parameters like this. Okay, and you can find the best solution. But the first idea, you know, to find this structure was done, okay, and all the structure was done by using first a topology optimization software. So in my team, okay, we construct also the thruster and we test it. Okay, so here you have a thruster, okay, made for Safran, okay, and we can test it in some like this, and we can test the magnetic field in some part of the motor to be sure that we did a good work of design. Okay, we can also simulate the aim. Okay, what is measured, okay, that's in red, what is simulating 3D in blue, okay, and simulating 2D, and okay, everything is very interesting. Okay, we are very close for all those kind of things, and of course we construct them and we gave them to Safran, and they can make some physical test, and you can see the blue zone here is about the projection of ions, okay, about 20 kilometers per second. That's quite huge, and that makes the thrust of our thruster over there. Okay, thank you for your attention. I can answer to some questions. Tell me.
Thank you, Professor Messine. So you decided to not interrupt our speaker during his speech. So maybe you have some questions now. Okay, so it sounds that you don't have questions about that. I just have one concerning the penalization function. For me, it looks like similar to the fuzzy logic methods. Is it something comparable to?
Okay, fuzzy optimization method could be applied, but okay, it's a bit different because fuzzy it's about a probabilistic thing, and we don't want to fix 0 or 1 at the beginning of fuzzy stuff. Okay, so maybe we can use fuzzy sets and representation to solve those kind of problems, but you have at the end to you know, fuzzy is about, okay, you are in between, but you need to push on the limit, and to push on the limit you have to add the penalization. Penalization is for the optimization, of course. You are inside the optimization, just to say with this penalization, okay, if you are in between, it's not good, that will be not the minimum. Okay, and you put that inside just to enforce the optimization code to converge to 0 or 1. That's the idea. If you use fuzzy, I don't know exactly, you can modelize your problem, you know, but you will still find solution in between 0 and 1, I think, at the end. And so at the end, the problem remains, and you have to make something to push the solution to be at the extremal part. Okay, I think. But I don't know a lot about the fuzzy methods. Okay, maybe I think that can be applied over them. Mm-hmm.
Okay, thank you very much. So if nobody have a questions or just a comment in the chat channel, okay, just congratulations.
Thank you. Thank you very much.
So thank you for all of you who have assisted in this presentation. It will be online on the YouTube channel on our R2P2 if you want to share it with colleagues and to see it again. So thank you very much and enjoy your day.
Thank
Bye-bye.
you very much. Bye.